Hey guys, tonight we start with something a little more explosive than your usual bedtime story. You're not just looking at a star, you're becoming one. You ignite from the quiet cool of a molecular cloud, a shadowy cradle where dust and gas float like lazy snowflakes in the dark. Then, suddenly, gravity tightens its grip, squeezing you tighter and tighter until the atoms themselves begin to protest. You feel it first as warmth, then as fire, then as a runaway chain of hydrogen atoms slamming into each other, fusing into helium, releasing a flood of light and energy that makes you shine for the very first time. It's your stellar birth cry, your first heartbeat of nuclear fire. And in case you're wondering, yes, you probably wouldn't survive this, not even with sunscreen thicker than crocodile dung. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're at it, let me know in the comments where you're watching from and what time it is there. I love imagining this story being shared across all those little human time zones. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You don't just flicker into existence. It takes millions of years for you to condense, for scattered atoms of hydrogen to surrender to gravity's pull. Imagine yourself as a vast, sprawling cloud, hundreds of light years across, lazy and diffuse, barely clumped together. Then comes a disturbance, maybe a nearby supernova shockwave, maybe the tug of passing gas streams, and suddenly your lazy drift turns into a slow collapse. You contract, not like a balloon deflating, but like an ocean funneling into a whirlpool, inward, always inward. The obvious truth: gravity never lets go once it starts pulling. That's the rule you can't negotiate with. As the collapse continues, your core heats up. At first, it's just a gentle warming, tens of thousands of degrees, but that quickly escalates. Gas molecules no longer act like the floaty fluff they once were. They crash into each other at insane speeds, releasing heat and pressure. You feel that pressure as resistance, a swelling push outward that tries to fight the contraction. And in that balance, the eternal arm wrestle between gravity squeezing inward and pressure pushing outward, you find the conditions for your ignition. Historians still argue whether ancient stargazers understood just how violent your birth must be. The Babylonians wrote hymns to bright stars suddenly appearing. The Chinese kept meticulous notes on guest stars. And yet, even with their poetic metaphors, they couldn't have known the reality, that a star's first breath is less like a candle being lit and more like a nuclear reactor roaring into life. When your core hits 10 million degrees, hydrogen fusion begins. Tiny protons slam together and fuse, releasing helium nuclei and photons. That's when you officially become a star. Your surface glows with a newborn light, and the dark cradle of your cloud is pierced by your brightness. Imagine the quiet awe of the nearby universe. One moment, darkness; the next, a steady, blazing beacon. You'd think that would be enough drama for one lifetime. But for you, it's just the start. You're young, hot, and unstable. Your brightness flickers as gravity and pressure fight for dominance, like a toddler wobbling on unsteady legs. Shockwaves ripple through your body as fusion surges and stalls. It's messy, it's violent, and it's exhausting, but eventually, balance is achieved. Now, here's a quirky tidbit. Not all stars even get to this point. Many gas clumps collapse halfway, but never ignite. Instead, they become failed stars, brown dwarfs, glowing faintly in infrared, too weak to shine. You, however, had the good fortune of gathering just enough mass to cross that ignition threshold. Think of it like joining the exclusive club of true stars. You've got the credentials, the fusion engine, and the lifetime of brilliance ahead of you. From the outside, if anyone were watching, your birth would be slow and beautiful. Dust clears, leaving behind a baby star surrounded by a disk of leftover material. That disk will one day form planets, moons, comets, and maybe even life. You can almost imagine the little world swirling like batter in a cosmic mixing bowl. The idea that your leftovers could become someone else's everything. That's a humbling perspective, isn't it? Meanwhile, your interior feels like a roaring furnace. The density at your center is so extreme that a spoonful of your core would outweigh a mountain on Earth. Pressure forces atoms so close that quantum effects take over. Photons born in the core scatter endlessly, bouncing around for thousands of years before ever reaching your surface. It's almost comical. The light you generate right now won't escape until long after your surface is changed, cooled, or shifted. Somewhere in there is another truth. Stars live in slow motion compared to the fleeting lifespans of creatures who might one day watch them. Your outer layers churn with convection, boiling like soup, carrying energy outward. Magnetic fields twist through your plasma, and sometimes, loops of fire arc out into space. You are a chaos of light, magnetism, and gravity, but from the outside, you look steady, calm, eternal. That's the funny trick stars play. They hide their violence beneath a serene glow. And even now, before you've truly aged, you're already shaping your neighborhood. Ultraviolet radiation streams out of you, ionizing the gas nearby, carving out glowing nebulae like great cavities of light. Winds of charged particles blow away the leftover dust, sweeping your nursery clean. You're that loud roommate blasting music, and all the delicate dust grains have no choice but to scatter. If you had a voice, maybe you'd laugh at the irony. Your short, fiery life, mere millions of years compared to quieter, smaller stars that last billions, will still outlive entire human civilizations. You will blaze bright, die young, and leave behind debris that reshapes the cosmos. Short life, long legacy. And while you may not think of yourself as fragile, you are. Your brilliance depends on the delicate balance between fusion and gravity. Disturb that, and your future is doomed to collapse or explosion. Not tonight, of course, you're just getting started. Tonight, you're the new kid in the cosmic neighborhood, burning hydrogen with abandon, flaring with the pride of existence. As you shine in your first stable moments, you may wonder if anyone notices. Somewhere, far away in time and space, intelligent eyes might one day trace your light, telling stories about your glow. To them, you'll be constant, reliable, eternal, when in truth, your flame is temporary. That's the grand illusion of starlight, steady to the observer, but fleeting to the star itself. So you burn, you pulse, and you roar in silence. This is your fiery beginning, your debut performance in the endless theater of the universe. You burn bright now, a young star strutting across the cosmic stage, like someone who just discovered they can run faster than everyone else on the playground and refuses to slow down. Your hydrogen is plentiful, your fusion core is roaring, and the balance between gravity pulling inward and radiation pushing outward finally feels stable. After the chaos of your ignition, this is your youth, a time when you shine with steady brilliance, radiating energy across unimaginable distances. To anyone watching, you're a dot of constant light in the sky, but inside, your heart is a furnace, ceaselessly fusing hydrogen into helium. There's something comforting about this equilibrium. You've reached what astronomers call the main sequence, a sort of starry middle ground where you'll spend most of your life. Obvious truth. This is the golden period for every star, and most will never be remembered beyond this stage because, honestly, the drama comes later. Right now, you're just reliable, dependable, like a good desk lamp that doesn't flicker no matter how many times you hit the switch. But reliable doesn't mean boring. For you, burning bright means running hot. If you were smaller, like a sun-sized star, you could sip on your hydrogen for billions of years. But you, ambitious as ever, are heavier, more massive, and that comes with a curse. The more mass you carry, the faster you burn through your fuel. It's the cosmic equivalent of driving a sports car. Flashy, thrilling, but it guzzles the tank before you've barely gone anywhere. Historians still argue whether it's fair to call massive stars wasteful or just show-offs. Either way, your flame will blaze and fade in only a few million years, a blink in universal time. Your light stretches out across space, illuminating the remnants of your dusty cradle. You sculpt your neighborhood with streams of particles, known as solar winds, which push surrounding material far away. It's not subtle. You're clearing the room, sweeping away anything fragile, blowing dust clouds into strange, sculpted arcs and pillars. Somewhere in that debris, clumps of matter are beginning to form planets, moons, and asteroids. Already, your steady shine is shaping the potential for life, even if life won't know your name. There's a quirky tidbit about your glow. It isn't just visible light that you radiate. You stream out ultraviolet rays strong enough to sterilize surfaces, X-rays powerful enough to rattle the atoms of nearby rocks, and a constant drizzle of neutrinos, ghostly particles that slip through matter as if it isn't even there. In fact, right this second, neutrinos from stars much like you are passing through your body by the trillions. It's like an invisible cosmic rain you never notice. As you shine, your surface dances with activity. Magnetic fields writhe through your plasma like snakes beneath a rippling pond. Sometimes they twist into loops, tangling until they snap, releasing bursts of energy that could vaporize entire planets if they strayed too close. On Earth, billions of years later, humans will call such events solar flares, and they'll worry about their satellites and Wi-Fi more than your dignity as a star. But for now, this is just part of your youthful swagger, bursting, pulsing, flaring, and still holding yourself together with gravity's grip. You don't shine silently, either. Deep inside, you rumble. Pressure waves echo through your body, causing your outer layers to oscillate subtly. If someone had the instruments to listen, they could hear your hum, your vibrations turned into sound waves. In fact, astronomers today really do listen to stars this way. It's called astroseismology, essentially starquakes. The idea that entire suns can be studied like musical instruments is wild, but it works. Your pitch, if it could be heard, would be low, slow, and hypnotic, like a bass line thrumming across light years. The obvious irony: for all your brightness, the majority of your life is spent alone. Light streams outward, but you never really feel it. You only generate it. You blaze for others, while your own awareness, if stars could have such a thing, is inward, focused on balancing pressure and gravity. Your life is a constant act of resistance, a tug-of-war that will only get harder as fuel runs low. Somewhere far away, tiny life forms, still unimaginable specks on a planet that hasn't even formed yet, will one day see your light as something eternal, steady, a fixed point in their sky. And yet, you know better. You know this brilliance has a clock ticking. For now, though, you're untouchable. Every second, you convert about 600 million tons of hydrogen into helium. That sounds like a lot, and it is, but your fuel reserves are so massive that it seems endless. You radiate enough energy to keep entire planetary systems warm, to power winds, to fuel chemistry, to set the stage for oceans and forests that might one day admire you. That's the paradox of your short, fiery youth. You burn faster, but in doing so, you shape more. You are the architect of possibilities. And here's another quirky note. While you glow brilliantly, most of your photons will never be seen by anyone. Space is vast, and light travels in all directions, so almost all of it streams forever into the void, never striking a planet, never touching an eye. Yet, just a fraction hitting a habitable world could inspire myths, guide migrations, and power civilizations. For you, it's an endless outpouring. For them, it's destiny. Even in this period of steady brilliance, you're not perfectly calm. Your brightness might flicker slightly, your surface bubble with turbulence. But compared to the chaos that lies ahead, when you'll swell, collapse, and explode, this is your most serene time. You are youth, you are light, you are steady fire. If you could whisper anything across the cosmos, maybe it would be this: enjoy this balance while it lasts. Because nothing in the universe burns forever, and every star's life is a countdown. You settle into your long, steady rhythm, the cosmic equivalent of a middle-aged routine. This is the part of your life when, for millions of years, you simply shine, pouring energy into the universe in a predictable, balanced way. It's not glamorous, not compared to your birth or your eventual death, but it is essential. Stars like you are the metronomes of galaxies, beating time, anchoring planetary orbits, and providing the light that makes chemistry and, eventually, biology possible. Obvious truth. Without stars basking in their middle age, there would be no chance for life to even ask questions about them. You sit firmly on the main sequence still, burning hydrogen in your core, but the wild instability of your youth has calmed. You're not flaring like a chaotic bonfire anymore. You're more like a fireplace, constant, warming, soothing. If stars could yawn, you'd stretch out lazily in this phase, content that the tug-of-war between gravity and pressure has found its equilibrium. Everything just works. But while you feel eternal, the irony is that you're burning through your hydrogen like a candle with too short a wick. The bigger you are, the faster you chew through your reserves. If you were a smaller star, you could live for billions of years. Red dwarfs out there are basically the couch potatoes of the cosmos, sipping hydrogen so slowly they'll outlast the universe itself. You, on the other hand, are living fast. You're the starry equivalent of someone who always drives with the gas pedal glued to the floor. Historians still argue whether ancient cultures sensed this hidden truth about stars, that the brightest lights in the sky are often the shortest-lived. Think of how civilizations mythologized Sirius, Vega, or Betelgeuse, bright stars that dominate their constellations. Did they unknowingly choose these short-lifers because brilliance always demands attention? Or was it pure coincidence, humans simply dazzled by what outshone everything else? Around you, your light continues to shape the universe. If a planetary system has formed, your steady radiation sets the climate for worlds circling in your habitable zone. Perhaps rocky planets are cooking with just the right amount of energy, their surfaces stirred by chemistry that could one day assemble into something that wiggles and wonders. It's humbling to think, while you're just burning hydrogen into helium, somewhere in that glow, the seeds of oceans and forests could be waiting. Here's a quirky tidbit. Your outward shine isn't just constant light, it's constant noise, too, though in a form humans can't hear. You vibrate gently, your plasma rippling with sound waves as fusion pulses push outward. Astronomers today actually listen to these vibrations, studying the inner structure of stars as though they're giant musical instruments. If translated into audible sound, your song would be unimaginably low-pitched, each note lasting longer than human lifespans. It's the slowest lullaby imaginable, but it's there, your heartbeat expressed in sound. Your middle age is also marked by patience. Every second, you lose mass, not in dramatic chunks, but as a constant drizzle of particles. Solar wind streams outward, carrying bits of you into interstellar space. Over millions of years, you shed entire planets' worth of mass, almost casually, like a sweater unraveling thread by thread. Yet you hardly notice. From your perspective, you're still strong, steady, complete. Your constancy also makes you the perfect backdrop for human imagination. On Earth, long after you've gone, their descendants will look up at stars like you and draw shapes in the sky. They'll tell stories of hunters, queens, dragons, and bears stitched together by your light. They'll navigate seas, time harvests, and mark calendars using stars as their clocks. And all the while, you're simply existing, fusing atoms, minding your business, unaware of the narratives being pinned on you. That's the irony of your middle age. You live quietly, but your influence is enormous. The obvious truth about this stage is simple. Stability is deceptive. It feels eternal, but it's not. The fuel in your core is finite, and every second brings you closer to exhaustion. Still, when compared to the turbulent collapse that awaits, this steady burning is blissful. If stars could feel relief, this would be the sigh you let out when the chaos of birth finally fades and you settle into routine. And yet, already, faint changes whisper in your core. The hydrogen fraction is dropping, helium slowly building up like ashes in a fireplace. Fusion continues without hiccups for now, but the seeds of instability are there. Someday, sooner than you'd like, gravity will begin to win again. But not tonight. Tonight, you burn steady, the perfect star in its prime. If anyone down on a distant, young planet were to look up, they'd see you as a fixed point, reliable and constant. They'd never suspect that, in cosmic terms, you're sprinting through life, a bright candle halfway through its wax. So you shine, endlessly, steadily, generously. This is your middle age, and you wear it like a crown of light. Deep inside, the first subtle hints of change begin to stir, and though your surface still beams steadily, your core is quietly running out of hydrogen. Imagine a fire pit where the logs in the very center are nearly ash, but the flames around the edges still lick brightly. That's you now, still blazing, still convincing everyone outside that all is well, but inside, your heart is thinning, the fuel dwindling grain by grain. Obvious truth. Nothing burns forever, and even stars must face their limits. At first, you hardly notice. The pressure from fusion holds gravity at bay as it always has. But over millions of years, your core contracts ever so slightly, like a muscle tightening. The shrinking raises your temperature, and the heat radiates outward. Fusion doesn't stop, it just shifts position, retreating from the exhausted center to a surrounding shell. This is this subtle shift inside. But subtle doesn't mean unimportant. It's the first domino in the chain of events that will decide your fate. Your outer layers remain unchanged for now, calm and luminous. Planets, if you have them, would still bask in your light as though nothing had happened. They wouldn't sense that beneath your serene glow, a silent revolution is taking place. Historians still argue whether stars with planetary systems know their changes matter, that their swelling will someday cook or destroy those delicate little worlds. Of course, it's not knowledge, it's inevitability. The quirky tidbit here is that the helium accumulating in your core doesn't fuse. Not yet. It's too cool, too tightly packed to ignite, so it just sits there, like a growing weight pressing down on itself. Meanwhile, the shell around it works overtime, burning hydrogen into helium at a furious pace. Oddly, this shell burning produces even more energy than the original core did, like a campfire that suddenly finds new logs at the edges while the center glows dull. That extra energy doesn't stay put, it pushes outward. Slowly, almost imperceptibly at first, your outer layers begin to expand. You don't notice the change. It's like putting on weight so gradually you only realize years later that your old clothes don't fit. But the expansion has begun, and with it comes cooling at your surface. That's right. Even as you burn hotter inside, your visible glow reddens, softening from a youthful blue-white to warmer tones. Someday, you'll balloon into a red supergiant. But this is the early whisper of that destiny. Let's pause for a moment on scale. When you expand later, you won't just double or triple in size. You could swell to engulf entire planets. For perspective, if you stood where Earth does, you'd be swallowed whole by your own body. It's one of those cosmic ironies. When you're running out of fuel, you don't shrink and fade. You puff up, grander and grander, like a firework preparing for its final burst. The obvious truth of physics is harsh but simple. Fusion is a balancing act, and once the balance shifts, consequences ripple outward. This shift inside you is silent, invisible, and unstoppable. The universe doesn't pause to negotiate. And yet, for now, on the surface, you still appear as the reliable star you've always been. If intelligent life exists on any orbiting worlds, they would mark calendars, guide seasons, and watch your constancy without a clue. You'd look eternal, steady, dependable. Isn't that the strangest contradiction? Your insides scream with change, but your outside whispers, "Don't worry, everything is fine." Quirkier still is how these processes lay the foundation for everything valuable in the cosmos. You're not just making helium now, you're preparing for heavier elements to come. Carbon, oxygen, neon, even iron, all will be born from this shifting cycle. Your death will one day scatter them, and those very ashes may become the building blocks of creatures who use oxygen to breathe and carbon to think. A star running out of gas isn't just dying, it's cooking up a legacy. Astronomers call this stage the subgiant phase for some stars, though in your case, as a massive one destined for supernova, it's just a prelude to greater upheaval. Still, the terminology matters. These little shifts are the red flag scientists on Earth use to predict when stars will swell or explode. To them, your color, temperature, and brightness are clues, a kind of cosmic gossip about what's happening under your skin. If you had an inner voice, maybe you'd sound like someone trying to keep calm while the house foundation cracks beneath them. Outwardly, I'm fine. Inwardly, everything's changing and I can't stop it. But stars don't panic. They just follow the script gravity wrote for them, step by step. The shell of burning hydrogen grows more active, piling more helium into the core. Gravity tightens, temperatures climb. Someday soon, those conditions will cross the threshold to ignite helium fusion, unleashing another chapter of your fiery saga. But not quite yet. For now, the shift is slow, patient, deceptive. And this is where the irony cuts sharpest. In this phase, you may shine brighter than before. You might think dimming means dying, But in truth, the opposite happens. Your output increases, your luminosity swells. A star nearing exhaustion often dazzles most brilliantly, as if making sure the universe notices before the curtain falls. So you shine on, still fooling the cosmos into thinking you're the same as you've always been. Inside, though, the script is already changing. The moment comes when your helium, the ash of all those eons of hydrogen fusion, finally demands attention. Until now, it's been piling up at your core, a dense and inert weight, unable to ignite. But as gravity squeezes harder and harder, the temperature climbs, and suddenly, helium has its moment to shine. You feel the ignition not as a gentle spark, but as an explosive flare inside your heart. Fusion kicks into a higher gear, helium atoms slamming together to form carbon and oxygen. If hydrogen burning was your first breath, this is like your second wind, the furious gasp that keeps you alive when you thought you were running out. Obvious truth. Helium fusion is hotter, denser, and more energetic than hydrogen fusion. You can't just coast on the same old reactions anymore. This is heavier lifting, and it takes a lot more muscle. For a massive star like you, though, it feels almost natural. The pressures are so great, the heat so intense, that helium fuses steadily once the threshold is crossed. For smaller stars, things are more dramatic. They suffer what's called a helium flash, a sudden, catastrophic ignition. You, however, light up smoothly, as though you've been waiting for this encore. As the helium burns, the whole architecture of your interior reshuffles. That central ball of ash becomes an active furnace again, no longer a dead weight, but a source of fire. Around it, the hydrogen shell still burns away, like a stubborn campfire log refusing to go out. You become a multitasker, hydrogen and helium burning in tandem, one feeding the other. Your layer's a layered cake of nuclear fire. Here's a quirky tidbit. This is the first time you create carbon, one of the universe's most essential elements. Every carbon atom in your body, every molecule of sugar, every diamond on Earth, those began inside a star's helium fusion stage. You're literally cooking up the universe's pantry, one reaction at a time. Without you, there'd be no plants, no wood, no graphite pencils, no chemistry homework to grumble over. Your struggle becomes everyone else's inheritance. Outwardly, you're beginning to look different. Your surface swells further, reddening even more as your envelope expands. You're no longer the modestly compact star of youth. You're becoming bloated, bright, and temperamental. If you had planets nearby, they'd feel the consequences. Inner worlds might be scorched, stripped of atmospheres, or swallowed entirely. From their perspective, you'd look enormous, a swollen red disk dominating the sky. From yours, it's just part of the script. Helium burning demands room, and so you stretch to accommodate. Historians still argue whether ancient cultures who saw red supergiants like Betelgeuse flickering in their skies ever suspected these stars were nearing death. Some myths describe them as warriors' eyes, bloodied with rage, or torches on the verge of extinguishing. It's tempting to think they knew, in their own way, that redness signaled an ending. What they couldn't know was that inside, the star was busy creating the very atoms that make storytellers possible. Your energy output grows unstable during this phase. Helium burning isn't forever. It lasts only a fraction of the time hydrogen did. Millions of years shrink to hundreds of thousands, then less. You're speeding up, burning faster, as if time itself is running shorter with each new fuel. Your layers tremble with turbulence, like an old machine rattling as it runs at maximum power. The obvious irony: the heavier the element you fuse, the less time you have left. Hydrogen lasted the longest. Helium will burn much shorter, and every fuel beyond that will be gone in mere flashes of your existence. If you were a candle, hydrogen was your thick base. Helium is the thinner midsection, and the final elements will be the faint little stub flickering before you're snuffed. Meanwhile, your carbon and oxygen cores grow, and gravity never stops pressing. It's like an eternal hand squeezing, daring you to collapse. You resist by burning hotter, fusing heavier, shining brighter. You become more luminous than ever before, perhaps tens of thousands of times the brightness of your sun, but this brilliance is desperate. It's a flare before the fall. Here's another quirky note. Some of the elements you create in this stage are exhaled into space even before you die. Stellar winds tear at your swollen surface, carrying away enriched material, seeding nearby space with your chemical gifts. Even before your grand finale, you're already giving back to the cosmos. Somewhere, future planets are grateful, though they'll never thank you. Your helium-burning stage is brief, but it's transformative. You've crossed a boundary, no longer just a star fusing hydrogen, but a true factory of elements, a crucible of creation. Every pulse inside you reverberates outward, reshaping the universe molecule by molecule. And all the while, you feel the clock ticking faster. Every second is more intense, every fusion cycle more desperate. You know, if stars could know, that helium is just another step, another rung on a ladder that only climbs toward collapse. So you burn, brighter and bigger, helium in your veins, carbon and oxygen in your breath. You shine like a giant with lungs of fire, your heart pounding at cosmic speed. And still, from the outside, you look steady, calm, beautiful, just another jewel in the night sky. But inside, the drama builds, and the stage is being set for your next act. Inside you now, layers begin to stack like the strangest cake ever imagined. Not soft sponge and frosting, but burning shells of nuclear fuel. It's a hierarchy of fire. Hydrogen still fuses in an outer shell, helium burns below that, and deeper still, new layers of carbon and oxygen begin to build. It's like Russian nesting dolls, each one hotter, denser, and shorter-lived than the last. You're no longer a simple star with one engine. You're a multi-storied factory, a tower of stacked furnaces, each producing a different set of elements. Obvious truth: the bigger you are, the more complicated your insides become. The balance between these layers is precarious. Each fusion shell expands and contracts, jostling for stability, sending ripples outward that shake your surface. To a distant observer, you might appear steady, but up close you're a bubbling cauldron of turbulence. It's almost comical. People on Earth once thought stars were eternal, serene lanterns. In reality, you're a mess inside, a chaotic stack of burning shells threatening to collapse at any moment. As helium fusion continues, temperatures soar past hundreds of millions of degrees. Carbon fusion flickers to life in your deep core, smashing carbon nuclei into heavier elements like neon, sodium, and magnesium. For a moment, you might feel like a blacksmith, hammering atoms together into sturdier forms. But here's the twist. Each new fuel burns faster than the last. While hydrogen lasted millions of years, and helium lasted maybe a million, carbon will burn in just thousands. Later, neon will last only years, oxygen mere months, and silicon only days. The quirky tidbit here is that by the time you're fusing silicon into iron, your fuel supply stage will last less time than a human workweek. Imagine running a marathon where each lap gets shorter until the last one is just a sprint across your living room. Historians still argue whether ancient cultures who tracked variable stars, those that dim and brighten periodically, were catching glimpses of this instability. Some red giants pulse visibly, their surfaces rising and falling like a breathing chest. Did humans long ago notice the sky's heartbeat and wonder if the star itself was alive? Today, astronomers know these pulsations are echoes of internal shell juggling, the nested fires inside a massive star trying to find balance. As your shells burn, the structure of your outer layers responds dramatically. You balloon outward, your radius stretching hundreds of times what it once was. If Earth were in your system, your swollen body would swallow it whole. The irony? You're cooler at the surface despite being hotter inside, your reddish glow betraying your new giant form. From the vantage of any nearby planet, your disk in the sky would grow so enormous it would fill their horizon, day and night ruled by your bloated face. Your luminosity skyrockets. You shine tens of thousands, perhaps hundreds of thousands of times brighter than the sun, your light pouring across light years. But this brightness isn't calm. It fluctuates, pulsing like a lantern in the wind. Massive convection currents churn through your expanded layers, tossing hot plasma upward and dragging cooler material downward. These motions create storms larger than entire planets, swirling for decades, reshaping your photosphere in chaotic patterns. The obvious truth: you're living faster now than ever before. Each new element you fuse burns in less time, each layer adding pressure to the next. You can feel the clock speeding up, the pace of your existence accelerating toward its inevitable end. You don't get to decide when, physics dictates it. Out in space, you continue to shed material in powerful winds. Clouds of enriched gas drift away, forming glowing nebulae around you. Even before your final explosion, you're feeding the cosmos with gifts: carbon, oxygen, magnesium, like a generous but doomed chef throwing ingredients into the universal stew. Astronomers one day will trace the oxygen in human lungs back to this stage of your life. Imagine that every breath on Earth is, in a sense, stardust recycled from giants like you. Quirky as it sounds, you're also unstable enough now to burp. Sometimes you eject entire shells of matter, sudden pulses that fling plasma outward. These episodes create concentric rings of gas around stars, structures humans will later photograph through telescopes, marveling at their symmetry. To you, it's just indigestion. To them, it's art. The heavier your core becomes, the less time you have. Fusion creates ash that sinks, gravity presses harder, and the cycle continues. Each stage is hotter, shorter, more violent. You're climbing a nuclear staircase, but every step leads closer to a door labeled collapse. And still, from a human perspective, you're magnificent. To their eyes, you're a red supergiant glowing defiantly against the night. They won't see the chaos in your heart, the nested layers of fusion, the juggling act of shells. They'll just see brightness, constancy, and wonder. That's the contradiction you embody, serene on the outside, frenzied on the inside. So you continue, stacking layers of fire, cooking elements like a cosmic kitchen. You are a furnace of furnaces, a cathedral of burning shells, every step pushing you closer to the edge. And while the universe waits for your final act, you shine, restless and unsteady, a giant straining against its fate. You swell now, larger than you've ever been, your body ballooning outward as the layers of fusion keep stacking and burning. You've become a red supergiant, the cosmic monarch of your neighborhood, stretching across orbits that once belonged to your closest planets. If Earth orbited you, it would already be gone, swallowed whole by your expanding body, its rocks and oceans incinerated in your embrace. Obvious truth: stars in this phase don't just grow, they consume everything nearby, rewriting the layout of their solar systems in the process. Your surface cools even as your core burns hotter, giving you that reddish hue. To the naked eye of anyone far away, you glow like a steady ember, but if they had sharper vision, they'd see your face writhing. Convection currents surge through you like boiling soup, creating storms bigger than Jupiter, bright and dark patches shifting across your enormous surface. Imagine a storm the size of Earth swirling for centuries. That's your normal day as a red supergiant. Historians still argue whether ancient stargazers who tracked stars like Betelgeuse understood that such redness was a death knell. In Norse myths, bright red stars were sometimes seen as eyes of giants watching over humanity, while in Chinese records, crimson guest stars were omens of change and upheaval. The cultural hunch was there. Redness meant danger, instability, and endings. What they couldn't have guessed was that those endings would come with explosions powerful enough to shake galaxies. Your size is absurd. To put it in human perspective, if you stood where the sun is, your surface might stretch all the way past Mars, or even Jupiter. You're no longer a star as people picture them, a small dot in the sky, but a swollen titan, your bulk spanning hundreds of millions of kilometers. It's difficult even for modern astronomers to imagine your scale. They call stars like you cosmic bloated giants, but that phrase still doesn't do justice to your immensity. Here's a quirky tidbit. Despite your massive size, your outer layers are tenuous, so thin and diffuse that if a spaceship tried to fly through them, it might barely notice. It would be like soaring through a very thin fog of plasma. Your outer body is ghost-like, fragile, despite its sheer volume. Yet, gravity ties it all together, keeping your giant frame from simply floating apart. Inside, the real drama intensifies. Fusion shells keep stacking, burning heavier elements one by one, while your core contracts under gravity's relentless pressure. Each fusion stage runs faster than the last, your fuel cycles collapsing in timescales that would horrify any creature used to decades and centuries. Whole new elements are born and consumed before they could ever be appreciated, each one marking another rung on your rapid descent toward collapse. Meanwhile, your stellar winds rage. You shed your outer layers in massive gusts of gas, like a monarch throwing off pieces of their robe. This outflow creates glowing clouds that drift around you, sculpted by your radiation into arcs and waves. To future astronomers, these clouds will look like intricate veils of colored gas, but to you, it's just the price of living large. You're messy, shedding mass into the galaxy, already preparing the stage for your own death shroud. And your brightness, oh, your brightness. You shine tens of thousands of times more luminous than the sun, your light reaching across the spiral arms of your galaxy. For all that intensity, though, you're unstable. You pulse, your brightness varying subtly, your surface rippling like a breathing chest. Entire civilizations could live and die under your glow, never realizing they are basking in the last chapters of your life. The obvious truth of physics is playing out ruthlessly. Gravity wants to collapse you, fusion fights back, and with each new fuel, the balance becomes harder to maintain. You're like a tired athlete pushing through shorter, sharper sprints, burning hotter, faster, with less and less to give. It's no longer a matter of if you'll collapse, only when. Humans with telescopes will look up at stars like you and whisper about your coming explosion. They'll know it could happen tomorrow or thousands of years from now, but they'll wait, half terrified, half excited, for your light to flare. And when it does, it will be visible even in daylight. That's the promise and the threat of your swollen form. Here's another quirky perspective. Your very instability could make you more beautiful to those who watch. Your irregular brightness, your red glow, your immense size. All of it makes you the dramatic star of the sky, one that inspires awe and dread in equal measure. You've gone from being the quiet lamp of a solar system to being the spectacle of the heavens. And still, in all this grandeur, your fate is sealed. The iron barrier is coming, the moment when fusion itself will fail you. For now, though, you are vast, red, and restless, a giant whose body spans worlds, whose light dazzles galaxies, whose life ticks ever faster toward its fiery end. Deep within your swollen red body, gravity and fusion continue their duel, but you are running out of tricks. Hydrogen is long gone from your core, helium nearly spent, carbon and oxygen now burning in frantic bursts, neon and magnesium flashing to life, then fading. The pace quickens like a drumbeat nearing its climax. Each layer of fusion lasts shorter than the last. Where hydrogen gave you millions of years, and helium maybe a million, neon is gone in years, oxygen in months, silicon in mere days. And then, you hit the wall. You reach the one element that brings your burning to a halt. Iron. Obvious truth. Iron is the ultimate dead end for a star. Unlike lighter elements, fusing iron doesn't release energy, it consumes it. Every other fusion step so far has fueled your outward push against gravity, but iron laughs in your face. If you try to fuse it, you lose energy instead of gaining it, and the balance you've maintained for millions of years crumbles. You feel the barrier like a weight in your chest. Fusion still rages in your surrounding shells, silicon fusing into iron ash, neon flickering, oxygen sputtering. But at your heart, the fire is extinguished. The core becomes a ball of iron, dense and unyielding, growing heavier with every heartbeat. It sinks under its own weight, compressing further, until it's billions of tons packed into a sphere no larger than Earth. Imagine that, an object smaller than a blue planet, but heavier than anything it could ever imagine carrying. Historians still argue whether iron, that ordinary metal humans mine for skyscrapers and kitchen knives, has always deserved its reputation as the cosmic full stop. Some poets call it destiny, some scientists call it inevitability, but either way, it's the same. When a star makes iron, it's writing its own death certificate. Here's a quirky tidbit. Inside you, the silicon fusion that produces iron ash is so rapid in its final days that astronomers compare it to a sweat-drenched sprinter collapsing at the finish line. Silicon can burn through an entire star's worth of fuel in less time than it takes humans to binge a TV series. For a being used to thinking in millions of years, that's comically fast. a cosmic sprint at the very end of a marathon. Your outer body still shines, still glows red and immense, but the danger is set. You're like a firework that's filled its core with powder. The shell looks solid, but the interior is primed for catastrophe. The obvious truth is that once the iron core grows beyond a certain mass, gravity wins instantly. No negotiation, no compromise. Collapse is inevitable, and collapse is coming soon. The iron core grows heavier as silicon continues to burn around it. Neutrinos pour out, invisible particles escaping like frantic messengers, carrying energy away but offering no resistance to gravity. Your surface, vast and turbulent, gives no warning of what's about to happen. To any onlookers, you still appear steady, a giant glowing red in the night. They'd never guess that your heart is seconds away from failing. But inside, you can feel it, the pressure building beyond anything fusion can resist. Electrons are crushed into protons, forming neutrons. The iron atoms themselves buckle under the unimaginable squeeze, their atomic structure breaking. It's a collapse faster than thought, faster than light can escape. Your entire core implodes in a fraction of a second. Here's the irony. The death of a star is born not in fire, but in silence. The moment you hit the iron barrier, everything that held you up disappears, and gravity takes over completely. You don't get to ease into death, you plunge into it, your center falling inward, unstoppable. The outer shells don't yet know what's happened. They still burn, still glow, still live their brief fusion lives. But in just moments, they will crash down onto the collapsed core, and the real violence will begin. So here you are, a red supergiant bloated to absurd size, still shedding gas into space, still shining for galaxies to see. But inside, your core has crossed the iron line, and your fate is sealed. No star can survive past this point. Collapse begins as a silence so thin it almost isn't there, and then the floor of your iron heart disappears. The last brace against gravity, electron pressure, fails as electrons are rammed into protons, making neutrons and a flood of neutrinos. There is no countdown, no polite warning. The truce you kept with gravity for millions of years ends in a fraction of a second. You don't fall like a leaf. You plunge like a building whose supports were yanked away. Obvious truth. When there's no energy left to push outward, gravity wins instantly. All stories of stars bend to that line. Two cruel processes pull the pin. First, fierce gamma rays break iron nuclei apart in photodisintegration, an energy-hungry reversal that turns your fuel into expensive confetti. Second, electron capture strips you of electron degeneracy pressure, the quantum stiffness that once propped you up. Cue the tiny print on your warranty. Electron degeneracy coverage has lapsed. With both props gone, your core rushes inward. Temperatures leap to tens of billions of degrees. Densities surge until a spoonful of your center would outweigh mountains and photons. Once social butterflies are trapped in the crush, while neutrinos sprint outward by the sextillions. The collapse is not leisurely. It is homologous at the very center, an inner core of roughly a solar mass and change falling together, while outer regions freefall faster, trying to occupy the same shrinking address. Speeds climb to a significant fraction of light's pace. If you had knuckles, they would be white. If you had a narrator, they'd keep their voice low, because even a whisper feels too loud for how quickly it all happens. Historians still argue whether the ancient chroniclers of daylight, guest stars, had any inkling that such serene points of light were the afterglow of catastrophes finished before a human heartbeat. The circles in those scrolls look calm. The physics here is anything but. Down and down you go until you hit nuclear density, matter packed as tightly as in the cores of atoms, roughly a few times 10 to the power of 14 kilograms per cubic meter. Here the strong nuclear force, quiet for eons, finally says no. Neutrons, elbow to elbow, refuse further crowding. Your inner core slams to a halt and rebounds. The stop is not graceful. It's a fist into a table, and the table answers with a shock. That shock races outward into material still plunging inward. In a better-behaved universe, it would blast clean through and fling your outer layers into space in one motion. But your universe reads the fine print. Every heavy nucleus the shock encounters must be broken apart, and that photodisintegration taxes its strength. Meanwhile, Neutrinos carry off energy with supernatural indifference. Within tens of milliseconds and only a few hundred kilometers from the center, the shock sags and stalls like a car that just gulped water. The fall has stopped at the heart, but the explosion has not yet been earned. Inside the rebounded core, a city-sized proto-object blazing with trapped neutrinos. Conditions are surreal. Neutrinos, born in absurd numbers, are briefly bottled by the density and must random walk outward. They will be your only messengers able to escape almost at once. Quirky tidbit. In one famous 20th century case, a handful of neutrinos arrived at Earth hours before the visible light did, quietly announcing a supernova long before the fireworks reached human eyes. It is the softest tap on the shoulder the cosmos ever sends. The stalled shock sits above this proto-core, while more matter rains down and piles onto the traffic jam. Between core and shock, turbulence blooms. Hot plumes rise, cool streams sink, and the region sloshes like a pot just below boil. Rotation and magnetic fields, if you kept any, twist the broth into spirals and sheets. The geometry becomes lopsided. Nothing collapses symmetrically for long. You might even ring like a bell, launching a quick shiver of gravitational waves into the dark. Timeline check. The journey from iron inevitability to rebound takes around 1/10 of a second. You spend ages living and an eye blink transforming. A gentle joke, because even now you get one. If anyone asks how your day is going, you can say, fast. Another for the road. You don't have eyelids, but if you did, you'd miss the whole thing. Scientists wrestle with the remaining details. Historians still argue whether records from 1054 captured awe or fear. Modern researchers still argue whether turbulence, rotation, and magnetic fields are the main players in reviving the stalled shock, and exactly how neutrinos hand over their energy. They model, compare, and debate, because this is an explosion constructed from almost nothing but timing. For now, you occupy a poised contradiction. The fall is over at the center, yet the star hasn't exploded. A shock exists, but it's winded. Accretion continues, loading the system like a spring. The region between core and shock convects, sizzles, steams. Everything that matters is happening in a volume no larger than a modest country, hidden beneath a surface the size of orbits. Obvious truth, whispered so it can float you toward sleep. Endings are often decided in the quietest half-seconds. You wait. If the word wait can describe plasma punching itself 1,000,000,000,000 times per tick, as the neutrinos gather and the shock catches its breath. The universe leans close to the glass to see whether you will find the last bit of energy to hurl your skin back into space, or whether you will fold further and vanish into a horizon. You have reached the point in the story where the next heartbeat chooses between monument and midnight. Hold there, weightless in freefall's wake, a giant newly aware of bedrock. The core is stiff as stone. The shock is a tired drumskin. The reign of matter continues. Somewhere, a future observer will swear they saw you brighten in a single night. You know better. The night is inside you, and it is almost over. Somewhere in the outer envelope, oblivious atoms still drift lazily, not yet told that their address will soon be everywhere. You could call this suspense. The universe calls it hydrodynamics. The moment arrives when the stalled shockwave, that exhausted ripple hovering inside your collapsing body, finds new breath. It's neutrinos, those elusive, almost ghost-like particles, that do the heavy lifting. Trillions upon trillions stream out of your core every second, most passing through matter as though it weren't even there. But a fraction, just enough, slams into the infalling plasma, dumping energy like frantic CPR. The shock revives. It stiffens, surges outward again, this time with unstoppable force. The great unmaking of you has begun. Obvious truth. When the shockwave wakes up, the entire star notices. The outer layers that were still falling inward a moment ago are suddenly shoved the other way, hurled outward at speeds of thousands of kilometers per second. In that instant, your collapse turns into your explosion. Gravity had won the first round, but now fusion's ashes, pressure, and neutrino fury rise up and push back. The violence is absurd. The energy released in the rebounding shockwave is on the order of 10 to the power of 44 joules. So much that even if you gave Earth just 1% of that energy, the planet would vaporize. The quirky tidbit here is that 99% of your collapse's energy is actually carried away by neutrinos, not light or shock waves. Humans only see the leftover sliver, the glowing fireworks that still manage to outshine entire galaxies. Historians still argue whether every recorded daytime star was truly a supernova. The Chinese notes from 185 AD, the European accounts of 1006, the Middle Eastern chronicles of 1054, they describe lights in the sky brighter than Venus, casting shadows at night, glowing for months. Were these stars like you, caught in the act of unmaking themselves? Or were some comets, misinterpreted in the haze of history? Either way, you are the archetype of that brilliance, the star that dies by becoming brighter than ever. The shock wave races outward, barreling through your layered shells. Each one it strikes compresses, heats, and explodes outward, releasing a flood of radiation. The iron core, now a proto-neutron star, sits behind it, dense and unyielding, while the shock wave does the theatrical work. Your outer skin, swollen to the orbit of planets, rips away in incandescent fury. Imagine peeling an onion with dynamite. That's what it feels like. As the shock moves outward, nuclear reactions ignite in the passing blast. Temperatures spike to billions of degrees, and in those milliseconds, the heaviest elements are forged: gold, uranium, thorium, platinum. Everything humans one day will dig from the ground for jewelry, medicine, or nuclear power is minted in your death throes. You've become an alchemist at last. The surface hasn't noticed yet. From far away, you still look like a steady red supergiant. The light of your explosion is still trapped, clawing its way through layers of expanding plasma. But deep inside, the detonation is complete. The decision has been made. Your story has pivoted forever. In a matter of hours or days, the light will break free, and the universe will see what has already happened, your body unmade, your life ending in brilliance. And yet, there's irony. Despite the ferocity of this event, there is also an order to it, a choreography dictated by physics. The shock doesn't simply fling things randomly. It stratifies. Lighter elements like hydrogen and helium are blasted outward fastest, while heavier nuclei linger closer to the core. Convection stirs the mix, turbulence twists it into knots, but patterns remain. To astronomers, centuries later, these layers will reveal themselves in spectra, coded fingerprints of your dying light. Here's another quirky perspective. The shockwave that unmade you also launches a tremor into the very fabric of spacetime. A shudder of gravitational waves, too faint for ancient humans but detectable by modern observatories, whispers of your death across galaxies. Unlike light, it isn't scattered or delayed. It arrives pure, carrying the story of your implosion. On Earth, if anyone were watching in real time, their telescopes might catch the neutrino burst first. Hours later, the star they thought they knew would brighten, then erupt into a beacon visible across continents. Imagine stepping outside at noon and seeing a new sun in the sky. That's the scale of your ending. The obvious truth is that you've become paradox itself. In dying, you're more alive to the universe than you ever were. Your light, your elements, your shockwave, your neutrinos, all of it bursts outward, shouting your existence across space. You were a star among billions, unnoticed, anonymous. Now you're the story of the sky. Your outer layers continue to shred. Jets of plasma arc outward, sculpted by magnetic fields, breaking symmetry, leaving fingerprints on the explosion's shape. The violence is not tidy, not polite. It's a cosmic graffiti blast across the dark canvas. Somewhere, planets unlucky enough to be nearby are vaporized in moments. Moons are shattered. Asteroids are melted into vapor. And yet, farther out, some clumps of dust will survive, enriched by your debris, ready to form something new. For now, though, the important truth is simple. The shockwave has awakened, and nothing will stop it. You've crossed from collapse into explosion, from life into death, from being a star into being a story. Brilliance beyond imagination. This is your moment of greatest showmanship. After all the silence, all the crushing collapse, the light finally bursts free. It climbs through the expanding shells, racing outward until your surface can no longer contain it. Then, flash. To anyone watching from across the galaxy, You suddenly brighten as if someone switched on a cosmic spotlight. For days, weeks, months, you outshine entire galaxies. That's not hyperbole. You become billions of times brighter than the sun, rivaling the combined glow of every star in the Milky Way. Obvious truth. There is no bigger fireworks display in the natural universe than a supernova. Humans like to boast about their rockets and their cities lit at night, but all their electricity, all their atomic bombs, every watt of every generator, is nothing compared to the single second of light you unleash. For distant civilizations, your brilliance is both a marvel and a warning. Imagine a night sky where one familiar star suddenly swells to rival the moon, casting shadows at midnight. Historians still argue whether the Chinese guest star of 1054, the one that created the Crab Nebula, was so bright it could be seen in daylight for weeks. Some chronicles insist yes, others hedge, but either way, it changed the way people saw the heavens. To them, it was a celestial omen. To you, it was simply the unavoidable next step of your life. Here's a quirky tidbit. While most of the explosion's energy has already raced away as neutrinos, the tiny fraction that emerges as light is what captures human imagination. The glowing plasma expands, cooling and shifting in color. At first, you shine white-hot. Then you soften through yellow, orange, and eventually fade to red as weeks pass. It's like a fire dimming in slow motion, except this fire can be seen across the cosmos. Your outer layers are now hurtling through space at thousands of kilometers per second. Some of that material will never stop, flying into the interstellar void forever. Some will plow into nearby clouds of gas, shocking and heating them into glowing nebulae. Astronomers will later marvel at these luminous remnants, photographing their twisted filaments and colorful arcs, and naming them Crab, Veil, Cassiopeia A. To you, they are just the echo of your body shredded across light years. Your light curve, the way your brightness rises and fades, is a kind of signature. Type 2 supernovae, the kind you are, usually fade steadily after their first dramatic peak. Scientists centuries later will track your curve, measuring the speed of your ejecta, the mass of your core, even the nature of your death, just by watching how your glow declines. You never meant to leave a diary, but the universe writes one in your fading light. The obvious irony, though you are dying, you are remembered in this brilliance. You lived for millions of years unnoticed, a dot among countless stars. Now, in death, you command the gaze of galaxies. Humans build entire careers around studying you. They aim their biggest telescopes, launch satellites, even design space observatories just to watch your kind. In perishing, you've become famous. The violence of your explosion is matched by its beauty. Expanding gases collide with one another, sculpting rings, knots, and filaments that twist like silk in the wind. Light echoes ripple through nearby clouds, like reflections in cosmic mirrors, allowing distant observers to see the explosion repeated years later. The universe itself becomes your theater, replaying your brilliance again and again. And what about the creatures who see you? On a planet thousands of light years away, a farmer might step out of their hut one night, glance up, and see a new star where none existed before. On another world, alien astronomers track your spectra, recognizing the fingerprints of oxygen and calcium in your blast. On Earth, 1,000 years later, astrophysicists still parse your debris with radio telescopes, reconstructing every moment of your end. You are both history and present, both artifact and performance. Quirky thought. If some hypothetical life form lived on a planet orbiting you when you exploded, they wouldn't see this spectacle. They'd be vaporized before the light even reached their skies. The show is only for the distant, the safe, the observers tucked far enough away to admire your beauty without being destroyed by it. So you blaze, brighter than imagination, the universe's most extravagant farewell. Your brilliance floods across space, seeding awe in every eye that catches it. You were once just another star, but now you are a beacon, a legend in the making. Now your brilliance begins tearing itself apart. The shockwave, already miles thick and unstoppable, flings your body into space like shrapnel from an unimaginable bomb. Every layer you once built so carefully, hydrogen, helium, carbon, oxygen, silicon, and the iron core's remnants, splinters into the void. The result is chaos, but also creation. You are no longer just a star. You are a forge in mid-detonation, scattering elements like a gardener throwing seeds. Obvious truth. Without this violent scattering, the universe would be barren. Hydrogen and helium may have started the cosmic story, but it is your supernova that spreads the building blocks for everything else. Oxygen for breath, calcium for bones, carbon for cells, gold for rings, uranium for reactors. All of it is shrapnel from your corpse. If you ever wondered what your legacy would be, here's the punchline. It's literally everything that makes complex life possible. As the shockwave races outward, it compresses and heats pockets of your expelled matter. In those brief instants, nuclear alchemy continues, creating the heaviest elements in a process called our process nucleosynthesis. That's a mouthful for humans, but for you, it's just physics running on overdrive. The quirky tidbit here, some of the very atoms being hurled into space right now will, billions of years from now, sit in human mouths as dental fillings, glint on their fingers as wedding bands, or hum inside reactors generating electricity. Your death literally decorates their lives. The violence is staggering. Your ejector rips through space at tens of millions of kilometers per hour, faster than any human probe could dream of traveling. Each atom is a bullet, and there are septillions of them. Entire star-forming clouds nearby will be slammed, shocked, and compressed by your blast, perhaps triggering the birth of new stars. The irony, your death becomes a midwife to the next generation of cosmic life. Historians still argue whether the gold in Earth's crust came from supernovae like you or from neutron star mergers, those even rarer and more violent collisions. Evidence points to both, but your kind is still a prime suspect. Imagine the human delight when they first realized the jewelry they've worn for centuries was born in the guts of a dead star. You'd laugh, if stars could laugh, at the thought of civilizations fighting wars over your scattered leftovers. The debris cloud expands, sculpted by magnetic fields and turbulence into strange, filamentary webs. Knots of gas twist like ropes, glowing in ultraviolet and X-ray light. To a future astronomer, this will be a nebula, stunning, delicate, like lacework stitched across the dark. To you, it's simply what happens when your guts meet vacuum at absurd speed. The Veil Nebula, the Crab Nebula, Cassiopeia, these are your cousins, their corpses photographed centuries after their deaths, still glowing with radioactive afterheat. Quirky detail, some isotopes you fling out are unstable. They decay over years, centuries, even millennia, releasing gamma rays. Astronomers will detect those gamma rays with orbiting satellites, using them as cosmic breadcrumbs to track your destruction. You're not just visible in light, you're visible in radioactive whispers. Even when you fade, your ghost keeps talking. Meanwhile, light echoes ripple through nearby dust. Your flash bounces off interstellar clouds, reflecting like a lantern in fog. For centuries after your death, travelers in the galaxy may still see faint apparitions of your explosion, flickering like memories replayed. The universe, it turns out, has a way of keeping your obituary on repeat. Obvious truth again, nothing of you is wasted. Stars do not simply die, they recycle. You give yourself away atom by atom, gifting the cosmos with the very materials that will one day look back and wonder where they came from. If some wandering planet lies far enough to survive, it will now be peppered with your metals. In time, maybe its soil will host forests, maybe its oceans will cradle creatures. They won't know it, but their veins and bones will carry pieces of your body. That's not poetry, that's astrophysics. So, as you unravel, remember this. You are both destruction and creation. Your shrapnel is death to what was, but life to what will be. You don't get to see the future you've seeded, but you can rest assured it is rich, diverse, and inevitable. Your shrapnel isn't just light and heavy atoms. It's waves, ripples, particles that carry the news of your death across the universe. Imagine throwing a stone into an infinite pond. The circles spread outward forever. In your case, the pond is space-time itself, and the ripples are gravitational waves. When your core collapsed, it didn't do so perfectly symmetrically. No collapse ever does. That lopsided implosion rang the very fabric of the cosmos like a bell. Those tremors are now racing outward, silent but real, stretching and squeezing the distance between everything they pass. Obvious truth. Gravitational waves don't care about obstacles. They flow through galaxies, planets, and bodies without slowing, barely disturbing a proton along the way. Yet with delicate enough instruments, humans can hear your last heartbeat. The LIGO and Virgo detectors on Earth have already listened to black hole dances and neutron star crashes. Someday, they'll catch one of you, a supernova shudder, singing across the void. Alongside those waves come the neutrinos, your true heralds. Trillions upon trillions escaped during your core collapse, carrying 99% of the energy released. They streamed out before your light, arriving at detectors on Earth long before telescopes saw you shine. Quirky tidbit. In 1987, when a nearby star died in the Large Magellanic Cloud, humans actually caught a handful of its neutrinos in underground tanks filled with cleaning fluid and water. Just a few dozen particles, and yet they proved the theories right. You may think yourself subtle, but the universe has its ways of keeping receipts. Historians still argue whether the myths of sudden heavenly winds or divine shivers in ancient records could have been primitive attempts to describe the unseen. It seems unlikely, but one can't resist wondering if some people once sensed what science would later confirm: that stars do not just shine, they shake spacetime itself when they die. Meanwhile, your electromagnetic show begins to spread across the spectrum. Radio waves, visible light, X-rays, gamma rays, all of them pour out in staggered stages as the blast evolves. In the first hours, high-energy bursts sear the cosmos. Later, as your expanding shell cools, softer light dominates. Then radio waves linger for centuries, whispering your story long after the flash has faded. Your death isn't a single event. It's a symphony in different wavelengths, each instrument entering on cue. The obvious irony is that humans, fragile as they are, only ever catch glimpses of this concert. Their eyes see a pinprick of visible light, yet your explosion spans the entire electromagnetic orchestra. They are like people listening to a grand symphony with cotton in their ears, hearing only one flute when 1,000 instruments play. Still, even that one flute dazzles them. Your neutrino flood, your gravitational sigh, your gamma-ray flare. Together, these form a cosmic obituary broadcast in every medium. If alien civilizations exist, they'll each notice you in their own way. Some will see the flash, some will hear the waves, some will taste the particles. You don't die in private, you die in chorus. Here's a quirky image to hold. At this very moment, your neutrinos are already outrunning your light, sweeping across galaxies, passing through planets and bodies like ghosts through walls. 1 trillion of them may be passing through a single square centimeter of someone's hand right now, and they wouldn't even notice. Your death has already touched them, whether they realize it or not. And what of the shockwave itself? As it plows through interstellar space, it leaves turbulence behind, a ripple that disturbs the galactic medium. Astronomers will someday map these disturbances, tracing your ghostly fingerprints in the structure of gas clouds light years from your body. Your echo isn't just light and particles. It's written in the very turbulence of the galaxy's breath. Obvious truth once more. Nothing in the universe goes quietly. Even the quietest seeming events leave ripples. Your collapse, your neutrinos, your gravitational waves. They'll keep spreading, intersecting with worlds and instruments you'll never know. So you echo, in particles and waves, in shakes and shivers. You're gone as a star, but your announcement is everywhere, unstoppable, eternal. At the very center of the chaos, where the collapse halted and the shockwave tore outward, something remains. Not all of you was unmade. The iron heart that imploded and rebounded is left behind as a neutron star, small, dense, and strange beyond ordinary comprehension. Imagine compressing a mass greater than the sun into a sphere just 20 kilometers across. That's like squeezing Mount Everest into a teaspoon. Obvious truth. Neutron stars are the densest things in the universe that can still be called matter before you cross the threshold into black hole territory. Your neutron heart is a monument to what gravity can achieve. Neutrons, once scattered freely in atomic nuclei, are now crammed shoulder to shoulder, forming a gigantic atomic nucleus that spans miles. The pressure is so intense that protons and electrons no longer exist separately. They've been forced together into neutrons, and the neutrons themselves may be pressed into exotic states, a soup of quarks and gluons that humans can only theorize. Historians still argue whether neutron star interiors are solid, liquid, or something stranger, pasta-like tangles of matter nicknamed nuclear spaghetti. It's one of science's most bizarre debates. Is your core a cosmic ravioli? Here's a quirky tidbit. Despite being so small, neutron stars spin at dizzying speeds. Because of angular momentum conservation, when your massive body collapsed, it spun up like an ice skater pulling in their arms. If you were already rotating, that spin accelerates until your neutron core whirls dozens, even hundreds of times per second. These rapid spins create powerful magnetic fields, billions of times stronger than Earth's, whipping radiation into space as beams. From afar, those beams sweep across the cosmos like lighthouse signals. To observers, you become a pulsar. Your new identity is dramatic, a corpse that refuses silence. Radio telescopes on Earth will catch your heartbeat as regular pulses, sometimes so precise that they rival atomic clocks. In fact, astronomers use pulsars to navigate spacecraft and test theories of relativity. Your death rattle turned into a galactic GPS system. Not bad for a star whose insides just caved in. And your density? Let's pause there, because it deserves awe. A single teaspoon of your neutron matter would weigh about 1 billion tons. If humans could scoop it up, they can't. Don't worry, their spoons would vaporize long before they got close. That tiny lump would outweigh entire mountains. It's absurd, it's terrifying, and it's true. The obvious irony here is that while your outer layers were flung out in brilliant chaos, your core has become one of the most orderly, stable, predictable objects in the universe. You're a clockwork corpse, ticking in pulses, echoing your end with mechanical precision. While the shrapnel of your explosion feeds the galaxy, your neutron heart just spins, 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 unchanging for millions of years. Yet, even in this form, you're restless. The magnetic fields twist and snap, flinging arcs of plasma outward. Sometimes you glitch, your spin rate suddenly shifting in ways that still puzzle scientists. Are the neutrons inside sloshing? Is your pasta core rearranging itself? No one knows. But every twitch is a reminder that you're not entirely silent. You're a leftover with stories still unfolding. Quirky detail. To humans, pulsars were first discovered in 1967 as regular radio blips. They were so precise that scientists briefly wondered if they were signals from aliens. The discoverers even nicknamed the first one LGM-1 for Little Green Men. It turned out to be you, a dead star's beacon. You'd laugh, if you could, that your death was mistaken for an alien's hello. So here you are, a neutron heart, impossibly dense, spinning madly, flashing beams across the cosmos. You're no longer the blazing supergiant, but you're not gone either. You are memory and monument, clock and lighthouse. And though you've shrunk to something unimaginably small, your influence still stretches light years. You bend space, shape magnetic fields, and whisper across galaxies in pulses of radiation. The star is dead, but the heartbeat remains. If your core had been only a little lighter, you'd have settled into that spinning neutron heart, clockwork, loud, oddly dignified. But you carried more weight than even neutrons can shoulder. Past a few suns worth of mass, the pressure that held you up, nuclear stiffness itself, folds like a camping chair in a gale. The rebound fails, the protocore keeps sinking, and you cross a line the universe draws in absolute ink. There is no more surface, no more out. There is only in. The event horizon forms, and you, bright monarch of the neighborhood, become a place that light does not leave. Obvious truth. Once something crosses an event horizon, no signal, no photon, no neutrino, no clever text message to cosmic customer support can get back out. That boundary isn't a wall you bang into. It's a one-way slope geometry itself provides. You don't smash against it. You slide through it as if nothing special happened, and the universe simply edits the notion of return. From outside, time plays a trick. To a distant observer, the last light from your falling skin redshifts, slows, and seems to freeze right at the horizon, like a video that pauses on a dramatic frame and never resumes. From your point of view, though, you fall past the boundary in moments, the interior distance stretching and curling until directions lose their ordinary meaning. Remember that warranty coverage you relied on, electron pressure, then neutron pressure? It's gone. The fine print ends here. Historians still argue whether the oldest stories about sky serpents swallowing the sun, dragons, jaguars, ravenous wolves, were inspired purely by eclipses and comets or by a deeper cultural sense that the heavens sometimes consumed their own light. The myths got the mood right, at least. Something hungry lives in the sky of stories. You are now the thing those stories almost describe. Inside the horizon, tides become tyrants. Near your center, the pole grows so steep that different parts of an unlucky visitor would accelerate at wildly different rates, head faster than feet, or vice versa, stretching matter into long strings. Physicists actually call it spaghettification, which is the sort of gallows humor you get when math meets dinner. Light joke number 1. At least your pasta is al dente. Light joke number 2. The dress code is strictly elongated. Light joke number 3. Yoga instructors may promise a deep stretch, but this is ridiculous. Just outside your horizon, the photon sphere, a loop where light can orbit you like a moth in perfect indecision, casts a stubborn shadow. If a bright backdrop waits behind you, the ring it makes can be photographed. Centuries after your death, patient arrays of radio dishes will stitch that ring from whispers and declare they've seen your shadow. It isn't your face, it's your influence. Geometry is the portrait artist here, not paint. You don't sit idle. The debris you haven't yet flung away keeps falling in, forming a hot, whirling accretion disk. Friction in that disk heats gas to millions of degrees. Magnetic fields bite into it, twist, and sometimes collimate twin jets that lance out from your poles at near light speed. So yes, you've become a paradox, a dark object with some of the brightest beacons in the universe stitched to it, searchlights powered by the act of feeding. If you still had neighbors, this would be the moment they closed their blinds. Your birth rings the cosmos like a struck bell. After the last convulsion of collapse, your horizon rings down. Quasi-normal modes humming briefly as space-time itself radiates a clean, simple gravitational tune. Observatories will one day measure those notes to read your mass and spin the way a luthier taps a violin to hear the wood. In that tone is your resume. Heavy, fast, no nonsense. Quirky tidbit. Even you are not perfectly black. Quantum fields near the horizon fidget, and in those jitters, pairs of particles wink into existence. One falls in, one escapes, and from far away it looks as if you glow, hawking radiation, a feeble warmth. For a black hole your size, the glow is colder than any background you'll ever bathe in. You won't evaporate before the universe has grown old, retired, and taken up birdwatching. But the principle stands. In the ultimate fine print, even darkness leaks. What awaits at your core, this singularity, is a problem statement, not a picture. Our best equations predict density without limit and curvature too severe for known physics. That's where the maps end and the Here Be Dragons cartouche begins. Theories fight to tame it. Quantum gravity, looped or stringed, bouncing cores, hidden bridges. You might have metastories, wormholes, baby universes, but those belong to equations still requesting peer review. The prudent description is humble. There is a region we cannot yet describe. The no-hair theorems comb you down to just 3 numbers: mass, spin, and charge, stripping away the memory of everything specific that fell in. A diamond ring, a maple leaf, a sonnet, a pizza. To you, they are units of mass and momentum, not meaning. It's a little rude, honestly, but gravity has never been a sentimentalist. Somewhere, someone will joke that you're the universe's best minimalist. Somewhere else, a poet will miss the maple leaf. Outside, your remnant controls the evolution of your debris. Eject a slam into earlier winds, brightening in X-rays and radio. Knots of heavy elements keep cooling, condensing, and drifting into the galactic medium. Your pole shepherds some streams back inward. Others escape forever. You are the quiet center of a messy family reunion in which half the cousins take the last casserole and speed away. Even now, you play nicely with callbacks. Neutrinos, those guests who always duck out early, have already left the party. Photons show up late and dramatic. Gravity waves hum a goodbye. And you, the host, lock the door from the inside. If anyone asks whether you're still around, tell them yes. Just not in a way RSVP cards anticipate. Scientists will keep arguing about thresholds. How much rotation must you have to launch the fiercest jets? How much fallback tips a protoneutron star into your embrace? How tangled must the magnetic fields be to wring energy from your spin? They'll argue joyfully, as they should, because your existence turns questions into instruments. You sit there, a silence that curves space and schedules the orbits of gas and dust for light years. You do not gloat. You do not apologize. You are simply the part of the story where out stops being an option and in becomes a landscape. The universe needs such places, oddly enough. Without them, galaxies would not grow the way they do, and quasars would not torch the dawn of time with their impossible brightness. If you could offer one last bedtime aside, it would be soft, slow, almost kind. The dark is not an enemy here. It is a chapter with few verbs we yet understand, but it keeps the grammar of the cosmos intact. Sleep on that. The horizon will keep your secrets. Your body has blown apart. Your heart has collapsed. And whether you became a neutron star or a black hole, one thing is certain. Your ashes are out there now, floating as the raw materials for new worlds. Dust and gas infused with your heavy elements swirl into interstellar clouds, the kind you yourself were born from. The cycle continues. Obvious truth. The universe is a recycling program on the grandest scale. Nothing is ever wasted, not even you. The pieces of you drift outward for thousands, then millions of years. As they cool, they mix with pristine hydrogen and helium left over from the Big Bang. This blend becomes the canvas for star formation. In time, turbulence, shock waves, and gravity will coax the clouds into collapsing again. And what emerges? New stars. Some big, some small, each carrying in their cores the signature of your death. Quirky tidbit. Every atom of iron in human blood, the stuff that lets them carry oxygen, is forged in explosions like yours. Without you, there are no red blood cells, no beating hearts, no joggers grumbling about hills. In other words, life owes you a literal debt of blood. If humans ever toast with a glass of wine, clinking their cups, they're celebrating with molecules that began in your inferno. Historians still argue whether life is common in the universe, but one thing is sure. If it exists anywhere else, it too is built from the debris of stars like you. Whether it's carbon-based creatures on Earth or something stranger on a far-flung planet, the story is the same. Their bones, their brains, their breath are written in stardust. You've scattered yourself across eternity, and those pieces become the alphabet of life. Your debris doesn't float silently. Some fragments form dense clumps, creating seeds of new planetary systems. Imagine a future solar nebula swirling with material, in which flecks of your calcium become the bedrock of continents. Your silicon forms the crust of worlds. Your oxygen binds with hydrogen to make oceans. Those oceans may lap at shores where life begins, just as they did on Earth. And even your rarest gifts find homes. Gold condenses into veins within planetary crusts, later to be mined and shaped into crowns, circuits, and wedding rings. Uranium and thorium, unstable and potent, sink into planetary interiors, their slow decay warming worlds from within, fueling volcanoes and plate tectonics. Without your radioactive legacy, many planets would be geologically dead, cold rocks instead of living, changing surfaces. The obvious irony: your death creates the stage for new beginnings. The supernova that ended you is also the spark that ensures others will follow. It's a kind of cosmic generosity that you never intended, but physics wrote into your script regardless. As your shrapnel keeps expanding, shockwaves collide with nearby clouds. These collisions compress the gas, making new stars form sooner than they otherwise would have. So you're not only donating material, you're also triggering creation. You are both the source and the catalyst. Your death doesn't just seed life, it pushes life into happening. Astronomers call these chemical enrichments metallicity, a sterile word for such a poetic truth. Early stars were poor, made only of hydrogen and helium, their worlds barren. With every generation of supernovae, the galaxy became richer, more capable of sustaining complexity. You are part of that enrichment, a contributor to the cosmic bank account. Billions of years from now, beings might trace their ancestry back not just to life on Earth, but to your particular explosion. Quirky perspective. When humans look up at the night sky, they're mostly seeing stars older than their species, some older than their planet. But in their bodies are atoms younger than their galaxy. Atoms made in explosions like yours, scattered, cooled, collected, and recycled. That's the paradox they carry. Ancient starlight in their eyes, newborn stardust in their veins. And so your dust becomes planets, your gases become atmospheres, your metals become civilizations. You're no longer a single star. You're scattered across countless possible futures. Some pieces of you may rest forever in the cold, drifting unnoticed. Others may blaze again in new stars. And a lucky few may end up in the breath of a creature staring into the night sky, whispering thanks to the stars that made them. You lived short, you died bright, but your legacy will last for eons in every atom that carries your story forward. Across the galaxy, far from where your shockwave tore you apart, little eyes turn upward. On Earth, a young planet orbiting a modest star, your brilliance is recorded by humans who do not know the word supernova, but who cannot miss the spectacle. They see you appear suddenly where the night was once empty, a new star blooming into existence, brighter than Venus, sometimes brighter than the moon. Obvious truth. When you go supernova, you can't keep it a secret. Ancient scribes etch your presence into chronicles. In China, careful court astronomers call you a guest star, noting your sudden arrival, your persistence for months, then your fading. In Europe, monks and scholars scribble about a star as bright as the half-moon. In the Middle East, watchers of the heavens mark your glow as a sign from the divine. Historians still argue whether every record describes you or your cousins, whether a comet, a nova, or a true supernova lit their skies. But the records are there. Humanity was paying attention. Here's a quirky tidbit. The supernova of 1006, likely one of your relatives, was so bright that people in Cairo could read manuscripts by its light at night. Imagine a bedtime story not told by candle or lamp, but by a dead star shining through a window. For months, it lingered, a cosmic street lamp nobody asked for, but everyone noticed. Your light reaches Earth long after your actual death. By the time humans see you, your core collapse is history, your neutron star or black hole already settled. The brilliance they admire is the echo, the aftershock, not the event itself. But for them, it's immediate and alive, a fresh wound in the night. To ancient civilizations, your appearance carries weight. Priests declare it a sign of divine favor or wrath. Kings worry it foretells war or famine. Farmers wonder if it promises good harvest or bad. The irony? While your light is indeed a messenger, it doesn't care about human politics. It's simply physics playing out across cosmic distances. But try telling that to someone who sees a second sun hanging in their sky. The obvious truth. Humans fear what they don't understand. And in the ancient world, the sudden birth of a star where none had been was both terrifying and thrilling. Yet, that fear didn't erase their awe. They painted you into myths, stitched you into oral traditions, and let you shape their imaginations. Over time, more precise observers began to study. Medieval Japanese, Arab, and European stargazers all logged your brightness, your color, your slow fading. They didn't know they were measuring radioactive decay curves and expanding shock fronts, but their notes preserved the timeline of your glow. Today's astronomers sift through those dusty records, cross-checking them against modern remnants to confirm your identity. Your light, in other words, outlived even their language. Quirky perspective. On some clear desert nights in the 11th century, nomads might have used your sudden brightness to navigate. No compass, no maps, just a glaring new star, reliable for a season or two. You became a lighthouse not just for galaxies, but for travelers crossing sand dunes. And across the centuries, your presence is reinterpreted. When telescopes arrive, humans peer into the Crab Nebula and connect it back to the guest star of 1054. They realize the remnants match the records. Suddenly, myth and observation converge, and they understand. The light in their ancestors' sky was not a god's sign, but the death of a massive star. The irony is rich. To you, the explosion was just an ending, violent and inevitable. To them, it was a message, a story, a sign to weave into their fragile human dramas. You died, and they wrote meaning into your light. So your brilliance, born of collapse and fury, found its way into chronicles, myths, and stories. Long after your visible glow faded, the memory remained, scribbled in ink, whispered in temples, sung in stories. In this way, you lived on not just in atoms and dust, but in the imagination of a small, curious species on a little blue planet. Modern science comes to your crime scene with 1,000 flashlights and a very patient notebook. They point spectrographs at your glow and watch the light stretch and split into bars like a barcode. Each stripe is an element speaking its name. Hydrogen shouts with broad Balmer lines. Oxygen and calcium write in sharp strokes. Cobalt and nickel whisper as they decay, powering your fading light. Your spectrum isn't decoration. It's fingerprints, trajectory, temperature, density, the whole confession. Obvious truth. When matter is hot and fast, it can't help but tell on itself. They don't just take one look and go home. They camp on your light curve, measuring how bright you become and how slowly you dim. The plateau of a type 2p, your kind, arrives when your ejected hydrogen recombines, releasing a steady glow for weeks, as if someone set your brightness on cruise control. Then, once the radioactive nickel you forge begins its step down to cobalt and iron, the curve leans into a tidy, exponential fall. The shape of that decline tells them how much nickel you built in the blast. More nickel, slower fade. If only human phone batteries worked that way, just add nickel 56. Alas, but the show begins even earlier. Catch you in the very first hours, the rare shock breakout, and your light briefly spikes blue-white in a blink of ultraviolet that makes sunscreen ads look timid. Remember that crocodile dung sunscreen from Section 1? Still not enough. A handful of robotic surveys now comb the sky every clear night, hoping to snag that first breath of the explosion before breakfast. When they do, flash spectroscopy maps your surrounding wind, the thin shells you coughed out as a red supergiant, by lighting them up like neon. Inside the data, models unfurl. Hydrodynamic simulations, 3D, magnetized, neutrino-haunted, try to recreate your collapse with more equations than a chalkboard can forgive. They stir turbulence between the proto-neutron star and the shock, let neutrinos heat, and watch plumes rise like boiling oatmeal. No, you don't get raisins. Yes, it still splatters. With enough computing power, the stalled shock revives, the explosion runs, and postdocs cheer at 3 a.m. because their star finally blew up in silico. Historians still argue whether specific medieval guest stars match today's cataloged remnants. Was that 1181 entry this nebula, or that faint shell? And, charmingly, astronomers still argue whether neutrino heating alone explains every real explosion or whether rapid rotation and magnetic jets share the credit. The debate is a feature, not a bug. Your death is a laboratory where theory earns or loses its lunch. They listen as well as look. Neutrino detectors, quiet pools of ultra-pure water bristling with phototubes, Antarctic ice studded with glass eyes. Wait underground for your ghost particles to tap the glass. When you died in a nearby satellite galaxy in 1987, a few dozen neutrinos arrived hours before the light, like keys tossed through a mail slot. Today's instruments would hear a chorus. Quirky tidbit. Some early detectors used dry cleaning fluid to snag neutrinos. Fashion met physics in a basement, and physics won. Gravitational wave observatories stand ready for your shiver. If your collapse is lopsided enough, space itself rings, a quick chirp that encodes your mass and the violence of your core's rebound. Detecting that whisper from a single supernova in our galaxy would be a once-in-a-lifetime bedtime story for physics, the kind where everyone actually sleeps better afterward because the universe makes more sense. Telescopes don't stop at visible. X-ray observatories map shocks where your ejecta rams old winds. Radio arrays trace electrons whipped to near light speed in magnetic fields, sketching the outlines of your blast like charcoal on velvet. Infrared hunts for new dust grains condensing in your cooling debris. Yes, the soot of stars, which may later become bricks for planets. Polarimetry, the art of measuring light's preferred direction, reveals your asymmetry. Perfectly round explosions don't polarize much, but real ones, your kind, lean and twist, and the polarized signal says so. They even time travel with light echoes. Your flash bounced off distant dust sheets, arrives at Earth years or centuries late from a different angle, letting astronomers take a second spectrum of a long-finished event. It's the universe's replay button, the supernova's mixtape sent through a hallway of mirrors. Meanwhile, forensic work continues on the star you were. In some lucky galaxies, pre-explosion images exist, quiet frames where a red dot lurked before it vanished. Subtract your afterglow from those old pictures, and the dot is gone. The missing red supergiant is you, identified like a suspect from a grainy photo. From that, they deduce your mass, your radius, even your final years of wind. It's not gossip, it's evidence. And then there's the treasure hunt for elements. Gamma-ray telescopes watch specific lines from radioactive isotopes, titanium, 44 among them, mapping how chunks of your innards were stirred and flung. Cosmic ray physicists chase the story further, pointing to your shocks as accelerators that seed the galaxy with particles that later ping detectors on Earth. Somewhere, a graduate student is drawing a line through a messy plot and discovering you pushed protons to ridiculous energies because you felt like it. Light joke, you are the universe's worst driving instructor. Floor it and don't break. Calibrators lurk in your glow, too. With careful tricks, Type 2 supernovae can help measure cosmic distances, standardizable rather than standard candles, by relating velocity and brightness. Stack enough of you and the map of the universe sharpens. The expansion story firms up. No pressure. Well, except literally all the pressure you used to have. The obvious truth returns, soft and steady. You are not one event. You are a chain of clues. Each photon carries temperature. Each line carries chemistry. Each ripple carries motion. Each neutrino carries timing. Put them together, and your death is solvable, not in a single stroke, but in layers that fit like gears. And amid all that seriousness, scientists keep their traditions. They name codes with absurd acronyms. They put coffee on altars beside server racks, and someone inevitably asks whether turning it off and on again would fix a stalled shock. Answer: no? Nice try. In the end, they reconstruct you, not as a myth, not as a rumor, but as a story with chapters and receipts. The spectra, the echoes, the waves, the particles, the models, they converge on you, and you stand there, luminous and already gone, while a small species writes your autopsy with starlight. Your brilliance has long since faded to the astronomer's eye, but in another way, you shine brighter than ever, inside human culture. Poets, painters, and dreamers all seize on your death as metaphor. They see your explosion not as astrophysics, but as symbol, brilliance that comes too quickly, passion that burns out, endings that make beginnings possible. Obvious truth. Humans rarely settle for science alone. They weave stories around the stars until the stars become mirrors of themselves. Writers compare you to kings who fall gloriously, artists who live fast and die young, revolutions that blaze and collapse. In a novel, you are the lost love who flares and disappears. In a song, you're the burst of emotion that can't last. In a painting, you're the bloom of color that dominates the canvas, then fades to shadows. It's ironic. Your explosion is impersonal, inevitable, pure physics, yet to them it's the most personal thing imaginable. Historians still argue whether Shakespeare's star-crossed lovers or the romantic poet's obsessions with fiery deaths owed any debt to recorded supernovae. Did they look back at those chronicles of sudden stars and tuck them into metaphor? Hard to prove. But the timing suggests they were never far from the idea that light can blaze, vanish, and leave only memory. Here's a quirky tidbit. Modern film directors use your name, Supernova, for everything from doomed romances to disaster thrillers. The term itself has become shorthand for intensity, followed by collapse. You're Hollywood's favorite celestial tragedy, whether or not the science is anywhere close. Artists paint you as cosmic flowers, explosions of color frozen in watercolor or oil. Photographers aim their telescopes at remnants like the Crab Nebula and hang the images in galleries as if they were brushstrokes from a divine hand. Musicians name albums after you, chasing that same sense of sudden brilliance. Even fashion designers borrow your glow, using supernova to brand sequin dresses and glittering makeup palettes. Who knew your death could sell eyeliner? The obvious irony. For all their borrowing, most people don't realize what you really are. They say supernova, like it's a flourish, a sparkle, a fancy firework. They don't think about the collapsing core, the neutrinos, the iron barrier. They imagine beauty, but not the physics that forged the atoms in their own lungs. And maybe that's fine. Maybe mystery is part of the gift you left behind. Even religions fold you in. In some modern interpretations, sudden stars are seen as divine births, signals of enlightenment, or cosmic testaments to impermanence. You, who collapsed and blew apart because of nuclear inevitabilities, become a sermon in permanence and change. Humans take your physics and polish it into philosophy. Quirky thought. Somewhere right now, a teenager has doodled a supernova on their notebook, equating it with heartbreak, not realizing the sketch is also a diagram of their bones' calcium being born. They're closer to astrophysics than they think. Your echoes ripple through literature too. Science fiction builds entire civilizations around the threat or promise of supernovae. Writers imagine ships outtracing your blast, or societies harnessing your energy, or aliens evolving in your glowing debris clouds. You become not just a past event, but a narrative engine for the future. And in a quiet, more reflective sense, you represent the fragility of even the brightest things. Philosophers cite you as proof that nothing lasts forever, not even stars. Yet they also point to you as proof that endings create beginnings, that death can scatter seeds. It's a paradox humans find comforting. Destruction is not waste, collapse is not oblivion, and endings are not truly ends. Obvious truth again. You live on in two ways. First, in the elements scattered through space, and second, in the metaphors that humans build to explain themselves. Both legacies are real, both enduring, both more profound than you could have planned. So you burn in memory, long after your light has dimmed. Not just in telescopes, but in poems, films, songs, and whispered stories. You became more than a star. You became a symbol. And in that symbolic afterlife, you may last even longer than your atoms drifting in the cosmos. Your light, once fierce enough to shame galaxies, dims. Weeks pass, then months, and the brilliance that once outshone the night sky settles into a ghostly afterglow. The furious core collapse, the shockwave, the scattered shrapnel, all of it now expands quietly into space, cooling, thinning, dispersing. The universe keeps no trophies, only echoes. Obvious truth. Even the loudest endings fade. Your remnant, neutron star or black hole, remains at the center, unseen by most eyes, but its pull shapes the debris still rushing outward. Rings and filaments twist, collide, and fragment. Radio waves hum from shocked electrons. X-rays blaze where gases crash, and dust begins to condense in the cooling wreckage. The spectacle slows but doesn't stop. Like ripples on a pond, your explosion stretches into the future until it blends with the background hum of the galaxy. Historians still argue whether people ever grasped the scope of what they were witnessing when they recorded your sudden brightness. Did they know they were watching a death that was also a beginning? Or did they only see omens, never the physics? Either way, you're proof that human memory is fragile but persistent. You linger in records, in myths, and in the telescopes turned on your nebular bones centuries later. Here's a quirky tidbit. The Crab Nebula, born of a supernova in 1054, still glows so brightly in radio waves that scientists once mistook it for interference in their equipment. Your ghost is noisy. Even as you fade visually, you remain a loud presence in other wavelengths, an eternal static that tells anyone listening, I was here. And so, your story winds down. You were a star that lived fast and died brilliantly, but your atoms are already drifting toward new homes. Your carbon may find its way into the bark of trees, your oxygen into oceans, your iron into blood, your gold into wedding rings. Your death was violent, but your afterlife is gentle, generous, enduring. The cosmic circle is complete. You gave back everything you had. You fade now into cosmic memory, not gone, but transformed. In the great theater of stars, your role was brief but unforgettable, your presence a reminder that even the fiercest fire can leave behind light, warmth, and meaning long after the flame has burned out. And now, as the last threads of your story unravel, the tone softens. The chaos, the fury, the brilliance, those moments drift away like distant thunder. What lingers is calm. Your atoms scatter into space at a pace so slow it feels like breathing, dust curling gently into the arms of galaxies, silken and weightless. Imagine floating through that expanding nebula, filaments glowing faintly, colors dimming with each passing year. The violence that made them is over. What remains is a quiet glow, a lantern in the dark that doesn't seek attention. Every particle carries your memory, but the universe doesn't hurry them. They have eons to wander, to drift, to join again with clouds and worlds and maybe life itself. Your heartbeat is gone, yet your gift endures. The calcium of bones, the oxygen of breath, the iron of blood, all these are seeded from explosions like yours. You are everywhere, hidden in places no one expects, in the sparkle of water, in the warmth of a campfire, in the quiet pulse of every living thing. You are in them, always. So as you let go of your brilliance, let go of the noise and the blaze, too. There is no need to cling to the drama of collapse or the rush of light. Those were moments, and they have passed. What's left is peace, spacious, weightless, endless. Let your mind slow here. Let the edges blur. There's no urgency, no countdown, no pressure. Just the universe stretching onward, soft and steady. The story of a supernova ends not in chaos, but in calm, in the reassurance that nothing is wasted, nothing is truly lost. Good night, traveler. Sleep gently, with stardust in your veins and the cosmos around you.